And then that way, very quickly, we can make those adjustments and be like, oh, well, I know how to work this formula. I know how to rework this formula because I've done it before. And then when it comes to formulas like your losses, you know, P is equal to I squared R. Essentially what we do in that instance is we take our Ohm's law and implant it into our power formula, and that's how we get P is equal to I squared R. So we want to state and analyze the relationship between work, power, and efficiency. That's going to be the big takeaways here. You'll need to describe work, energy, and power. You'll also need to describe the relationships between them, okay, and how we can use one formula to get into another formula to get the final answer. And that's probably the tricky part here. Then we get to calculate efficiency and volt drop and line loss. So going through those calculations should be straightforward, I hope. When it comes to our grand universe, we have two basic components. We've got matter and we have energy. We know that matter can be changed into energy. Oh, there's a little. Darren, that's such a funny comment. Love it. So yes, and to answer your roommate, they already have, right? They already have. There was a comment saying that I talk like Michael Scott. So yeah, it's coming at me again. So we've got matter that can be changed into energy. Also, energy can be changed into matter. and then I laugh like Dwight. That's nice. So you can really see this if you've studied the atmosphere or really energy conversion in any minute sense. One of the fun things is just the sun and how it takes two elements and combines them, gets another one, and then we have this massive explosion of energy, right? And so we're taking matter and creating energy, fusion and fission, right? This is that type of conversation that we can have as well. But that's not this course, so we're gonna go to the next slide. When it comes to changes of energy, we do have these mechanical motions, right? We can change any one of these into the other. Okay, so heat or light can be changed into mechanical, mechanical can be changed into sound, sound can be changed into radio waves can be changed into heat or light, right? We have all of these conversions that can take place and all of the different elements that combine to do so. And for our purposes, we really want to make sure we understand this electrical conversion. What are things being converted into electrical energy? What are things being converted from electrical energy to mechanical, or from electrical energy to heat? That's how we get some of these losses, right? When we get to losses, that's what we're talking about. We're talking about electrical energy being converted to heat, which sucks because then we're losing part of what we actually want that thing to do, right? Like we're losing part of that current and it's just dissipating off into the world as heat. And this is why we loved incandescent lights, right? The little filament, those suckers get hot and your furnace doesn't have to work so hard because you got like 90 of these in your house. And so it's actually heating up the house. Funny story, that's a true thing. Like people noticed that their furnace bill went up when they switched their house to LED lights. It anecdotally has been reported. So just note that that's a real thing. And we get to play with kind of the hows and the why fors. Quick review, the quantity of matter, we call it mass, okay? And we measure it in kilograms, all right? So that's the basic things that you have to know. When it comes to weight, your weight is actually your mass combined with gravitational force. That's weight, all right? But your mass in and of itself, we would say absence of gravity, is also measured in kilograms. So, quick review. The amount of substance an object has is called mass. Due to mass change, does mass change due to laws of gravity? No. Weight. It's weight. Mass is measured in kilograms. Its symbol? Yeah, good job. Ta-da! Oh, hey, more review. Any type of attempt to change the relative motion of an object is called? What was that? Yeah, force. Good job. Because it's in the next question. Force is measured in? Yeah, if you haven't noticed, the answers are given away in the next question. What's force measured in? Newtons, yeah. And force is a what? Example? Good one, Travis. That was a good one. Directional, okay? Force is a direction. Got to have that direction there for it. All right. A measurement of force required to equal the force of gravity that exists between two masses is called, yeah, weight. Because it's in the next one. He's picking up how this works. I like that. So weight is measured in newtons of force and is commonly described in you guys are all looking for the answer in the next. It's there. You just have to. Kilos. Yeah. Kilograms. Nice. 1 kilogram equals. Yeah, it is. Yes, it is. All right. Quick example. See that example? It was just premature. Come a little later. So the Grocer's scale measures force in newtons, but the scale is calibrated to read in kilograms. So this is what you can see with those Grocer's scale. You have this force that is exerted down due to gravity. And we're not going to get into whether gravity is a push down or a push up. That's outside the parameters of this theoretical course. But if you want to talk with the big leagues, it's up, not down. Anyways, so we've got this gravitational force down, and we've got an equal force of the Grocer's scale going up, and that indicates to us that the scale's reading 4 kilograms. But the measured weight is actually 39.24 newtons. Okay? And that's just one of those examples that you can see for the Grocer's scale. The way that you would figure that out is you would have, it's kind of your ratio scenario, okay? So 1 kilogram over 4 kilograms, right? Because that's what the scale is reading, is equal to 9.81 newtons over the number of newtons. You guys follow? So we're doing one of those fancy ratio things. 1 over 4 is equal to 9.81 over n, which is our unknown. And when you do the math, it comes out to be 39.24 newtons. Using this cross multiplication is how you will solve a lot of your questions. Okay, this is kind of how they come at you. Is they give you a couple things and want you to find out another, and it's the ratios that you will use. On that note, excuse me, if a bag of sugar has a mass of 10 kilograms, what is its measured weight? Take a minute. Take, I mean, a second. For those of you who are really quick at math, yeah. 98.1 is our fancy answer. Okay. The reason being is we've got 1 kilogram over 10 kilograms is equal to 9.81 newtons over N. So to solve for N, you'd have 9.81 multiplied by 10 divided by 1. Okay? That's how you get 98.1. Just as a quick reminder for those of you who I'm going a little bit quick for, I am recording this lecture and we'll throw it up for you to review later. Okay. Next one. A dumbbell weighs, because we're all thinking about working out these days, right? Maybe not, maybe just me. 111.441 newtons. That's a very specific number, right? What is its mass? You're going to apply those same cross multiplication rules. 1 kilogram over our unknown kilograms is equal to 9.81 over 111.441. What do you get? Yeah, nice. 11.36 kilograms. Good work. Any questions on how we went about those answers? Cross multiply and divide. Yep, that's it. Good. So when it comes to mechanical energy, we've gone over what mass is and what force is, what weight is. When we talk about work in and of itself, this is going to be the thing that has to be done over a distance. Okay, so you have to have a force. It's going to have a direction. Remember, because force has a direction, either pull or push. And then it has to be done over a distance, or else you're not doing anything. So if I stand here and push against this wall, am I doing any work? As much as the yoga people want to convince me that I'm doing work right now, I am not, according to math. Okay? So that's how that will shake down. We'll get to that, Hunter. We'll get to why this has to do with electrical in a second. When it comes to work, it is force in newtons over or multiplied by a distance. That is your formula. It's one of those that you either can or cannot memorize, but that you should know, all right? Very simply. We're getting there. When it comes to energy, energy exists in two basic forms. You have potential energy, which is energy stored by the blank. What would that blank be filled in with? I got my handy mask. Position, right? That's it. And then kinetic energy is the energy stored or of the motion, right? So I can throw my mask and then we've got that motion. Okay. Now, answering Hunter's question, electrical energy conversion. Okay, so we have electrical energy. We've got some little points of work. Remember, going back to some basics, that energy cannot be created or destroyed. It will be changed from one form to another. And since energy and work share the same unit, it can be said that it takes 1 joule of energy to perform 1 joule of work. Okay? And it looks like this in formula. 1 Newton times 1 meter is equal to 1 Newton meter, right? That makes sense for units. And 1 Newton meter is equal to 1 joule. remember, work is equal to force times distance. That's how we get that top formula. And this is where we're going to take a few steps to get to the point of where this actually makes sense for us to be involved in these types of equations and to have this type of knowledge. To start, do an example. Okay? A 1,200 kilogram reel of cable is lifted up to the second floor that is 3 meters off the first floor. Hey, Zach, this is what you do. We got to lift a reel up to a higher floor, right? No, you never do that, hey? That's what you got Skylar for? Nice. Skylar, watch out. Yeah. So we got to lift this off the first floor, and what is the work required to do so? Once again, we go back to our basic formula. You write that thing down. Work is equal to force times distance. And then you plug in the numbers. We've got our force, 1,200 kilograms, times our newtons, 9.81. We're working against gravity, times 3. We end up with 11,772 newtons times 3, and then we get 35,316 Newton meters, or we can call it joules. Or sometimes the questions will be like, hey, throw this into kilojoules. Always, always, always check for what units they're asking you for, okay? Especially when it comes to the code tests, side note, because they will have you calculate everything in watts, but then they want your answer in kilowatts. Okay, so just be aware that that might creep up on you if you're not paying attention to what units they're asking you for. And I can't just like scoop up and give you an answer and be like, yeah, you get that 100% right. No, because you didn't read the question. So yes, yes. To finally get to Hunter's question, boom, electrical energy, hey? So it takes 1 joule of electrical energy to move 1 coulomb of electrical charge under a potential difference of 1 volt. That's a really fancy way to say that 1 joule equals 1 coulomb times 1 volt. Know this formula. It will be very helpful when you're trying to convert things on the exam. In essence, the joule is that unit that allows easy conversion between mechanical and electrical energy. This is that unit of measure that if we have that force in joules, right? Or that unit of measure in joules, energy, then we can convert it to, well, how much electrical energy do we need to move that thing or to do something with this object, okay? Yes. This may happen to you once or twice when you just confidently answer the equation. And I'm not sure if you guys have seen this show, but this is like quintessential what parents experience with education at this point, because they're teaching math differently. All right. So what is power? Whoa, back it up. There are 2 definitions that we have to consider when it comes to power, okay? Power, first of all, is the rate of doing work or how fast work is done, and the rate of energy conversion. In essence, power is the amount of work done in a certain amount of time. When you're measuring your meter on your house, it's what is the work that is being done by your dishwasher, by your range, by your lights, by your stove, by all those things in your house over time. And then we charge you for it, or the utility company charges you for it. right? And that's what we're talking about here. What is the symbol for electric power? It's a symbol. Watts. This is another one of those slides that'll give you the answer. Okay. How's it measured? In watts. Power can be mathematically expressed as P is equal to energy or work over time, which is equal to watts. So what the heck does that mean? We've never seen a power formula like this. My power formula is current times voltage, right? So when we look at the basics of this formula, 1 watt is the rate of 1 joule per second. All right. So power then is equal to force times distance, Newton meters or joules, over time. And this is going to be one of those formulas that you need to also know for conversion when you're trying to convert things from mechanical to electrical energy. Okay? Here's an example. Oh, that overlapped for some reason. I apologize for the messiness of this slide. Something shifted down. Actually, you know what? I'm just going to fix that. That's better. So if we have that same reel, 1,200 kilo, and it took 3 minutes to lift it 3 meters to the second floor, how much power was required? Step 1, write out your formula. Okay. Step 2, solve for work. Work is equal to force times distance. So 1,200 times 9.81 times 3. That will give you your Newton meters. And then you calculate the time in seconds. So if we have minutes given to us, we have to multiply it by 60 seconds to get 180 seconds. And then you divide work by time, right? And we get our watts. Is that process easy enough? Any questions about that process? No? Okay. What I want you to do then is take that process and take the next 5 minutes to try and solve these 3 questions. Okay. Skylar, did you do the first one?
Yes.
Okay, how'd you get it?
I did the kilograms times 9.81
Okay.
to get the force, and then times that by the 8 meters.
Okay. What'd you get for your answer?
235,440.
Perfect. That's what I got. I like it. I like it. Okay. Number 2. Justin, what'd you do? Get number 2?
I divided that by 180.
Okay. And what did you end up for watts?
1,308 watts.
Nice. Awesome. Okay. Trevor, what'd you get for the last part?
2,616.
Yeah, 2,616. How'd you figure that out?
I took the joule
Nice. Perfect. So if we wanted this work to be performed in half the time, we would need a motor that could deliver twice the amount of kilowatts. Okay? If we decrease the amount of time to do the work, this will increase the amount of power required to do the work. What do we call that type of relationship? When one thing goes down, the other thing goes up. What kind of a relationship is that? Inversely proportional. Thank you. Yep. Any questions on those questions? Okay. Here is the power formula that you might be able to recognize. Electrical power is produced by voltage and current. But the question really is, well, we've learned all this other stuff about newtons and time and all that other good thing. Where do we get this formula from? Where's this coming from? If we start with watts is equal to joules per second, and remember that joules per second, or joules is equal to coulombs times volts, then it can be said that watts is equal to coulombs times volts, okay, which is current, or coulombs per second is current and voltage over 1, right? Because that's what you got to remember, that amps is equal to coulombs per second. Okay? So this is how we get that formula of watts is equal to amps times volts. We just keep putting formulas in other formulas. That's how we get this. And you may, or may not, but probably, will be asked questions that will require you to know the ins and outs of how we got this formula. All right? And if it asks you what the coulombs are, and it gives you the watts and the volts, maybe a little bit of time, could you figure that out? Yeah. All right. So power then, in essence, is current times volts. If we want to get really fancy with it, you can rearrange the symbols around, and I just memorize it as pi. So if I think my power formula, a little bit of pi. Mind you, that's because I just love pi. It's probably the most addicting thing. A little bit of apple crumble, a little bit of ice cream, gotta be vanilla. I'm just telling you, melts, heated, of course, gotta have the pie warm. You know what I'm talking about, Brock. This is like the best thing. Yeah. This is what makes like holidays, right? Because you know that the apple pie is coming down the line and you know that mama made some ice cream. And this is, yep, just good. All right, other ways to find the power formula. Since I is equal to V over R, we can substitute that I for V over R. And in essence, get P is equal to V squared over R. Because we've got our W. Yeah, that's Spanish for W. You actually don't have a W. Sorry. You got your two V's, put them together. So what if we wanted to substitute for volts? Well, volts is equal to I times R. Then we can substitute that I times R in for V. And we get P is equal to I squared R. All right, let's do a couple more examples. Give you another 2 minutes to figure these guys out. All right. Bryce, what'd you do for number 1?
Was that one just 12 times 120?
Yep,
Okay. 1,440 watts.
that's it. Hunter, you didn't miss out much. We were just doing these example questions. We're just starting going through them. Yeah, that's correct. So you take your power formula, P is equal to I times E, and then you take your 12 amps, multiply it by 120, which gives you a power of 1440. Okay. All right, number 2. We'll go Nathan. What'd you get for number 2?
I didn't get that one.
Didn't get that one? All right. So when we have a rating of, let's see. Yeah, just making sure I'm reading everything correctly. So when we have milliamps and ohms, we're going to call this thing losses. Okay. If you hear the term, what are your IR losses or power losses? It's really dealing with this formula. So we're going to take our current of 0.5 amps. We're going to square that, and then we will times it by 100 ohms to give us our losses or our power rating or wattage rating of 25 watts. Okay, and that's how that one goes. Does that make sense? No. Did you do that way? No. He's got new ways of doing things. So that's what you got to do. P is equal to I squared R, or in other words, P is equal to 0.5, right? Because 500 milliamps is 0.5 amps. 0.5 squared times 100. For number 3, calculate the power of a 2 ohm resistor connected with 6 volts. So this will be just another iteration of that formula. We've got volts, we've got ohms. So we can say that our power will then be equal to our volts squared over our resistance, right? Pardon? Yeah. 18 is what you said? Perfect. That's exactly it. So 6 squared divided by 2, 18. For the final one, what is the operating resistance of 60 watt lamp at 120 volts? We've been given volts. We've been given watts. We have to transpose this formula to get R is going to be equal to E squared divided by P. Or in other words, 120 volts squared divided by 60, which will give you an ohmatic value of 240. It would be, so that's a really good question. If you're trying to find the volts, so let's say we've given you 240 ohms, but we didn't give you 120. Okay, what you would do is you would take your power of 60, you would multiply it by 240, and then you would have to square root that answer. Okay, that will give you your volts. So power times resistance square rooted. Right? I'm surprised you didn't wear it. Yeah, that's just inappropriate. Lastly, the total power in a circuit, whether it is series parallel or series parallel, is going to be found by adding up each of the individual powers. And it is that simple. Okay? if we have resistors in this series parallel format, we would just go the power of resistor 1 plus the power of resistor 2 plus the power of resistor 3, and you see how it goes. All right. I have an example for you, but they also give you examples in the book, so we're just going to cut it off there.